Okay, students, good morning to all of you. Am I audible to all of you?
Yes, ma'am.
Okay, so UG students, shall I wait for a few minutes or shall I start? Our students are going to join further. Okay, so let me add the PPT. So in between the students will join. Okay, so let us start. So good morning to all of you. So this is our fifth class, I think, and so today I'll try to just convince or I'll discuss with you the second module. I think the first module, 2-3 points I'll discuss maybe after the completion of this module. So as module is important for us because we are going to start our tutorial very quickly. So this module, based on this module, maybe 2-3 experiments we have. So for that reason, I'm interested to cover this module. So in the second module, we have the components of the smart grid system. So coming to the components of the smart grid system, the very important part of the components of the smart grid environment or technology or network, you can say, are the distributed generation resources. So what is this? The very important point next that it comes to your mind. What is this distributed generation resources? We call it some DGR or sometimes distributed energy resources. We call it DERS. So according to IEEE standard, also we call it as DERS. So D stands for distributed, E stands for energy, R stands for resources. So this distributed research energy resources are basically nothing. It includes the solar energy system, the wind energy system, the photovoltaic, the fuel cells, biogas, biomass, then small hydro. So all together, all the non-variable and variable renewable sources. And along with those renewable sources, we have also you have also the battery storage system. So we should not forget the battery storage system. Also, it comes under this category, the distributed generation resources or distributed energy resources. And apart from that, so these are I'm just coming to I'm just talking about the components of the smart grid technology. So if somebody will ask you, what are the components of the smart grid environment, then certainly it will come to our mind. The first one is the distributed energy resources. That will come to our mind. Solar, wind, you have battery banks, and you have photovoltaic, you have wind system, you have the fuel cells, and sometimes we have biomass, the small hydropower plants. So which are basically renewable in nature. Okay, so mostly as in the introduction section, I just emphasized on the point that basically the renewable sources are the major target in the smart grid technology. So therefore, if you're targeting the renewable sources which are going to be penetrated as much as possible in our existing network, So then only it will be a beneficial or advantageous fact for all of us. Otherwise, if you're not going to just attract the renewable sources penetration into our existing network, so this smart grid has no meaning. It is just meaningless because already this coal-based generation we have sufficiently 60%. I mean, we are just getting from that 55% almost, and again we are just trying to some take kind of the sources which are basically fossil fuel based, and from where we'll get maximum carbon dioxide emission, green gas emission process. So the pollution will be there, and some other situation will arise. So therefore, the major concern of the smart grid technology is to hire or to penetrate, to extract more and more energy from the renewable sources. So the major component of the smart grid system is nothing. The first number one, if somebody asks, that is the distributed energy resources. So it includes both the renewable sources as well as the storage platform. Now, so in this context, the components, if you say, further also we have electric vehicles, and further if you just move ahead in a very specific manner, if somebody asks me what are the components, I do agree with the concept that I said that the renewable sources and the storages are the major components. But if you go further deep, I mean into inner, definitely the electric vehicle will come one more important component of the smart. Because in electric vehicle case, what happens? Suppose you have the existing platform of vehicle is very horrible. I can say so this diesel, petrol, and also these are all in very. I mean that also. While I'll talk about the electric vehicle, I can show you what kind of scenario the India government and the whole world is facing for the diesel and petrol cost, and what kind of emissions we are getting. And if we replace that those with the battery renewable empowered electric vehicle system, then what kind of benefit we are going to get. So therefore, the next component which comes to my mind is the electric vehicle. This is another important component or resource, you can say, for smart grid network. And again, further if you move, you have further other appliances like smart transformers, and you have smart appliances means smart appliances means so many things. Home appliances you have smart money. So, but in general, so in this particular topic, we'll read the smart transformers, smart home appliances, then smart meters. So these are some of the smart devices which are also important key components or key factors, or you can say key devices of the smart grid network. And further again, if you'll just tell me, we have also sensors, intelligent sensors, controllers, intelligent controllers, adaptive sensors, adaptive controllers. And again, we have some kind of monitoring protection devices like micro PMUs, reclosers, relays. So these are some of the basic building blocks or components of the smart grid system. Okay, so without these components, if these components are absent, so then I cannot say the existing electric network as a smart grid network. So that second module concentrate on these components. Yes, of course, in this distributed generation resources, I will try my best because we have many modules. So this is not only the class which I will concentrate on the distributed energy resources. So these are the basic fundamentals we will gain. And individually, the solar wind itself is a very big topic. The solar energy itself is a one area of research and an area of thoroughly somebody should learn it. And wind energy's platform is also itself is a one thorough topic chapter. And your electric vehicle itself is one chapter. Battery storage is also one of the major chapter. So on. So what I'm trying to, convince or inform to all of you before going to the operation or the network configuration of the smart grid technology or its structure. So I'll just introduce all these components in a basic manner, and if somebody is interested, I can refer you some papers or some books if you're interested, research students or UG students. You can read further for your gaining more knowledge. So I put my best effort to inform the basic ideas of these components. So first, I discuss with all of you the solar energy system, because that is the largest energy system. If I'm not wrong, because in the first class of my introduction class, I said India is the leading energy. I think is the fourth. Now it is going to be third leading agency in the solar generation platform, and we have also a lot of facility, and we have resources are available. So that we have a keen interest towards solar generation. So this is a book all of you can write, Photovoltaics, Fundamentals and Technology and Practice by Konrad Mertens. So you can write this book name, and maybe you can download some PDF if it is available in the Google, or you can type it and you can replace Photovoltaics, Fundamentals, Technology and Practice. Some basics are provided in this book. It will be easier for all. And another book you can write, The Solar Energy System by Professor Solanki from IIT Bombay. So he has also written a good book on solar photovoltaic. Many books are available. You just type photovoltaic, basic fundamentals photovoltaics books. So many books will come. But the by Professor Solanki, which is written by from IIT Bombay professor, so he has written every basics from its design, its little bit operation, and its efficiency, curves, and all. So he has discussed in detail in that book. So, and that book, if we in the main process also, if possible, if it is, I think one of the students has taken it is possible in the library, I can take some snapshot I can send to you, which are essential for our study. Not all the chapters. So, few chapters may be helpful for us. So, this photovoltaics fundamental technology and practice you can read, and maybe you can refer many other books, conceptual things you need. Okay. So as I said, why do you put by this distributed generation resource? What is the meaning of that? The meaning is the DER are smaller power sources that can be aggregated to provide power necessary to meet the regular demand. Okay. So this is how this DER include any non-bulk electric system, non-bulk. It's not a bulk amount of power we are going to generate. We may be generating 100 watt, 100 kilowatt, 100 megawatt, it doesn't matter. But it is not in the range of gigawatts, some range of 50 megawatt, range of 20 megawatt. It is in the range of small range, very small range. Even why not one solar panel I'll just keep on the street light. So just to empower my lighting system, I mean, I'll have some storage, battery storage. So it will just enlight the lighting system during night time. And maybe sometimes in the the electric, I mean the traffic system, and if some signals required, some energy is required for the signaling. So from there I can take the rooftop mounted the solar panel. So very small energy is required over there in the range of watt. So therefore, it's a smaller power sources that can be aggregated to provide the power to the required demand places. It's not necessarily bulk. It is non-bulk electric system, and multiple generating units are a single location, and energy storage facilities there. And there is a microgrid concept comes from the micro means it is in the range of 10 to minus 6. A grid means in the power handling capacity range of 10 to 9. So I mean in the gigawatt. So therefore, if you multiply to minus 6, so it will scale down the power to kilowatt. So that microgrid concept we will learn in the third module onwards. So the micro means it's a smaller concept, smaller version of the grid. So when we scale down the power to a smaller version, its handling capacity, it is easier to handle, it is easier to install, it is easier to supervise. So it is easier to control, or some whatever the action we want to take, it will be easier for us. So therefore, this is only possible in smart grid and with help of the distributed energy resources. Solely look at solely in the boundary of any distributed utility. So of course, some utilities are there, some customers are there. So within their premises, it can be also located. So this DER, according to the IEEE standard, so the DER are generally interconnected to a distribution provider's electric system at a primary voltage of less than 100 kV or greater than 1 kV. Okay, or secondary voltage level that is less than 1 kV also. Like in IIT Roorkee, so our panels are installed at the 230 volt level, 440 volt level. So therefore, it can also be connected to the secondary voltage level and the primary voltage level. So it has it cannot be connected. It can be, but the point is its generating capacity is not more than 50 megawatt. That is the last boundary or target of this microgrid concept or DER's concept. So this is a non-bulk generation power unit. So this is keeping in mind. So we will decide what is the capacity of the solar park or wind park, or we have a small hydropower station, or we have a biomass system, or even then we are going to just connect some electric vehicles or storage facility inside my network. So based on that, we have to follow the guidelines. What are the power handling capacity of the network? So these are some of the installed capacity of the solar energy in our country. So more or less, we are targeting 20 by 2020 around 175 gigawatt of renewable energy, including the biomass, okay, and cogeneration, small hydro, and solar. And again, the wind also it is also there. So wind around 60 gigawatt, and solar is more because, as I said, we have a large potential sites inside our country where the solar energy can be extracted. This is how the solar resource map of India. So mostly the red side you can see, which is basically the larger resources of solar irradiance, where we have larger solar irradiance, and from where we can project, and our projects can be installed, or our major solar parks can be installed or targeted by the government of India. And mostly the Maharashtra, this western side, and few regions in the UP and MP, and here in the southern side. So they are more or less quite convincing for the solar irradiance prominent areas. So we have, more or less you can see here, 90% of our country, our geographical locations are suitable for solar energy generation. So this is a very good indication for all of us. And if we have good technology for all of us, then we can always meet our goal. The 170 gigawatt is not a very big amount for all of us. If we just all of us will be dedicated for generation, for utilization for every purpose. So mostly in the residential sectors, we aim for the DES like solar, small wind turbines, natural gas, and emergency backups. And in commercial industrial belts, we need solar voltaic, wind turbines, hydro, biomass, combined heat and power systems, fuel cells. So mostly what in this picture I just want to say, both in commercial, industrial, and residential, and transportation, and even agriculture also. So here I have not added 2 more points. So all the 5 sectors, there we can use the solar system. Solar system plays a great role in every aspect. So this is the solar scenario of our country, top 10 countries in the globe. The first is China. It is contributing around 26.2% of the whole globe. And the United States around 13.3% is, and India is around 9.9%, 9.8 gigawatt. That is around 8.6%. So what is the meaning of this? That if we'll try to basically utilize the solar sites of our country, so India may also cross US and China one day. Our population growth is also quite high, large. So exponentially our energy demand is increasing. So if we can properly install the solar plants, then hopefully we'll cross these 2 countries very soon. So now in this solar, one of the component of this renewable energy sources, that is DERs. is our solar energy system. In sometimes also we call it as a photovoltaic system. Okay, so this solar cell, what is that? Well, today I'll just tell you the basics, and then next class I'll just talk about its mathematical modeling aspects, and then its behavior characteristics, and then of course its efficiency, and then we'll wind off. Maybe 3 to 4 class I can devote because other components are also there. So this solar cell is a photovoltaic device. Okay, it's a photovoltaic. This photo and voltaic, these two words are different. Photo means it is the energy packets which are available in the solar irradiance, in the light system of the solar, in the light of the solar energy system. So that photon is basically packet of energy source. And voltaic means it's a chemical reaction. It happens within the PN junction. That I'll show very quickly. Maybe one video also clip I'm interested to show all of you, because the animation will be much clear for all of you to understand the concept. So this photovoltaic, photo and voltaic together means photo means the light energy and voltaic means the chemical energy. Then what happens when the photovoltaic, the light energy falls on a surface of the PN junction? What kind of chemical energy takes place? So that your it's a reaction basically. So due to that, current flow will be there. The voltage rise will be there. Okay, the voltage variance will be there. Potential difference will be there, and then from there will be a flow of energy, flow of current. So unless until you have some barrier, some driving force, then you cannot drive a current. So when there is a potential barrier and you have current, so product of these two is the energy or power. Okay, so this P is equal to V into I. So that means essentially, so this photovoltaic cell converts. It makes a conversion process from the light energy to the electrical energy, isn't it? So the solar cell. So if somebody asks you, it's a very simple way I can explain you that the solar cell, it converts like your motor generator. Generator converts the mechanical energy to the electrical energy, or motor, it converts the electrical energy to mechanical energy. So similarly, the solar cell converts the light energy to the electrical energy. So this electrical energy, how it is produced, quickly we'll just learn. So this is a effect. The photovoltaic effect is the basis of conversion of light into electricity in photovoltaic or solar cells. This light, which is pure energy, enters the PV cell and imparts enough energy to some electrons, negatively charged particles, to free them. And the built-in potential barrier inside the cell acts on these electrons to produce a voltage, so called as photovoltage. The voltage generated, it's called as photovoltage, and which can be used to drive a current. So that means it's a very, very positive sequence. You can think in a positive frame of mind. When the light falls, then the light energy has some energy process, and the electrons, free electrons, can be lost. It can move, the mobility will increase, and then some barrier is going to be created, that is a voltage difference will be created, and that will drive the flow of electrons, and that flow of electron means the flow of current. So then you have the energy above. So these consequences I'll show you in a like in this picture, but before that I just want to show one video. If whether I have to stop this, and again I'll come back to this, whether it will be audible or not, you so tell me, but it's a good thing if I can share that. Okay, so let me share that video. Is it my video? My video is seen to all of you? Is it visible?
Yes, sir.
Yeah.
2 decades, the contribution of solar energy to the world's total energy supply has grown significantly. This video will show how solar cells, photovoltaic cells, produce electricity. Energy from the sun is the most abundant and absolutely freely available energy on planet Earth. In order to utilize this energy, we need help from the second most abundant element on Earth, sand. The sand has to be converted to 99.999% pure silicon crystals to use in solar cells. The sand has to go through a complex purification process as shown. It's converted into a gaseous silicon compound form. Then mixed with hydrogen, you can highly purify polycrystalline silicon. Are reshaped and converted into very thin substances called silicon wafers. The wafer is the heart of a photovoltaic cell. When we analyze the structure of the silicon atoms, you can see they are bonded together. When you are bonded with someone, you lose your freedom. Similarly, the electrons in the silicon structure also have no freedom of movement. Let's consider 2D structure of the silicon crystals. Assume that phosphorus atoms with 5 valence electrons are injected. Here, one electron is free to move. In this structure, when the electrons get sufficient energy, they will move freely. A highly simplified solar cell only uses this type of check. When light strikes them, the electrons will gain photon energy and will be free to move. However, this movement of the electrons is random. It does not result in any current through the loop. Flow unidirectional. A driving force is needed. An easy practical way to produce the driving force is an E-N junction. Let's see how a P-N junction produces the driving force. Similar to N-type doping, if you inject boron with 3 valence electrons into pure silicon, this is called P-type doping. These two kinds of doped materials join together, some electrons from the N side will migrate to the P region and fill the holes available there. The depletion region is formed where there are no free electrons and holes. Due to the electron migration, the N side boundary becomes slightly positively charged, and the P side becomes negatively charged. And will definitely be formed between these charges. This electric field produces the necessary driving force. Let's see it in detail. When the light strikes the P-N junction, something very interesting happens. Light strikes the N region of the PV cell, and it penetrates and reaches out to the depletion region. This photon energy is sufficient to generate an electron hole pairs in the depletion region. The depletion region drives the electrons and holes out of the depletion region. Observe that the concentration of electrons in the N region and holes in the P region becomes so high that a potential difference will develop between them. Since we connect any load between these regions, electrons will start flowing through the load. The electrons will recombine with the holes in the P region after completing their path. In this way, a solar cell continuously gives direct current. So, you can see that the top N layer is very thin and heavily doped, whereas the P layer is thick and lightly doped. This is to increase the performance of the cell. Just observe the depletion region formation. Check out that the thickness of the depletion region is much higher here compared to the previous case. This means that, due to the light striking, the electron hole pairs are generated in a wider area. This results in more current generation by the PV cell. The other advantage is that due to the thin top layer, more light energy will reach the depletion region. Now, let's analyze the structure of a solar panel. You can see the solar panel has different layers. One of them is a layer of cells. You will be amazed to see how these PV cells are connected. Fingers, the electrons get collected in four spots. The top negative side of this cell is connected to the back side of the next cell through copper strips. Here, it forms a series connection. When you connect these series connected cells parallel to another cell series, you get the solar panel. A single PV cell produces only around 0.5 voltage. The combination of series and parallel connection of the cells increases the current voltage values to a usable range. The layer of EVA sheet on both sides of the cells is to protect them from shocks, vibrations, humidity, and heat. There are two different kinds of appearances for the solar panels. This is because of the difference in the internal crystalline body structure. In polycrystalline solar panels, multi-crystals are random bright. The chemical process of silicon crystals is taken one step further. The polycrystalline cells will become monocrystalline cells. The principles of operation of both are the same. Monocrystalline cells offer higher electrical conductivity. However, monocrystalline cells are costlier and thus not worth. Costs of PV cells are negligible. The total global energy contribution of solar voltaic is only 1.2%. This is solar panels and original homes have the option to store electricity with the help of batteries and supercharge controllers. However, in the case of a solar power plant, the massive amount of storage required is not possible. So, generally, they are connected to the electrical grid system in the same way that other conventional power plant outlets are connected. With the help of power inverters, DC is converted to AC and fed to the grid. Support that engineering educational activity.
So I hope all of you enjoyed the video. So, isn't it? What is your comment? Can I hear from anybody? Hello?
Yes, ma'am.
Can I hear from anybody?
Yes,
You got
ma'am.
it?
Yeah.
Yeah, got it?
Yeah, ma'am.
Yeah. Yeah. So any UG students? You got it? Some ideas? Any UG student can answer me? Can I hear from the UG students? Yes. So all of you listen properly? UG students? Okay, so now coming to the same thing, what animation you have seen over there. So what is the basic principle through which the solar cell acts? So as I said that this is known as solar photovoltaic. Okay, so photo means photon. It comes from the solar light energy, and when this light energy falls on the p-n junction, then it generates the electricity. I mean the whole free electrons, and those free electrons are basically driven by the potential barrier which is created within the p-n junction, and due to that p-n junction barrier, the free electrons, I mean the potential difference or that driving force basically drives the free electron from one terminal to other terminal. It will connect some loads. So it is quite interesting. If you see here, this picture I have just taken to make you more understandable. Let us see that I mean silicon is basically has the free electrons, but these are in bounded form, and that is not possible. I mean to create more free electrons and more free holes. The concept all of you know. I am not going to go in detail. That's a UG class stop in the second year power electronics. So this N type is basically doped with the phosphorus, and the P type is basically doped with a boron. So when these impurities are basically added with the pure silicon, so you'll get N type silicon and P type silicon. So when this N type and P type silicons are basically it is actually with the process of diffusion, it is contacted with each other, so the p-n junction is formed. So due to this p-n junction, so what will happen within this depletion region, the free electrons of the p-type and n-type and holes in the p-type, so they'll just try to combine with each other, and they'll prepare the hole and electron pairs. So that hole and electron pairs, that is known as depletion region. So it has some I forgot exactly what electron volt of energy. That is actually the that potential barrier which is basically created. It is in the range of 0.5 volt. Okay, so 0.5 volt DC, and that voltage which is basically the gradient which is generated inside this p-n junction or depletion region. So that is ready with some potential. But now we have to dislodge the free electrons from that region, so that the free electrons can move from one terminal to other terminal. So when this p-n junction is formed and the depletion region is formed, so what will happen? On the p side and the n side you have the plus terminal, and the p side you have the minus terminal, right? So what will happen? Now in the process of, and the top of it, the depletion region, you have the plus terminal, and the bottom you have the negative terminal. What will happen now when the light falls? So this light falls. So this light will penetrate, and it will slowly it will reach to the depletion region. So this point is important to remember. So this depletion region should reach, the light, the photons should reach to the depletion region, not P region, not N region, or nowhere. The main region where the light should reach, that is the depletion region. So before this, in the video, you could have seen that even though you have some N-type silicon buffer, you have silicon, you are adding some impurities like phosphorus, and you have free electrons. Even when you connect some load, then the free electrons are not going to flow because you don't have any barrier, you don't have any potential difference. You will try to drive the free electrons. The movement of free electrons is zero. The mobility of the free electrons is zero. Simply you take an N-type type silicon. So what will happen? Still then, even though you have free electrons, the free electrons are not going to flow even though you connect one. You connect one load across it. So therefore, we have to connect a plus and minus terminal. Then only there will be a barrier will be created. So therefore, we have to take N-type silicon and P-type silicon. Then we have to create a P-N junction barrier, and that P-N junction barrier will create a potential, and that potential difference, a barrier or that gap will, that driving force will be responsible to drive the free electrons, which are actually generated with help of the photon. So this photon, the light generates electron hole. So here it will just penetrate the N-type, because the N-type silicon is located on the top, and the P-type is the substrate, it's the base. So generally this P-type, N-type is very thin, and the P-type is very thick, because there are two reasons. It is, as you could have observed. The first reason is why this P-type is thick in nature, because we have to generate more electrons. More electron pairs will be basically prepared during the diffusion process of the p-n junction. So when this more electron electron hole pair will be generated, so when the light will fall on the diffusion region or depletion region, so more electrons are going to be lost, and then the flow of current will be higher, and the energy and the power content will be higher. So therefore, that is one reason. And second, why this N-type is thin? Because if you not make thin N-type, then the light should reach to the depletion region. But if I make the N-type more, thicker, and your P-type junction is, thin, so it doesn't matter. Then the current will not, the light will take some time to penetrate to the depletion region. So if it will be thick, it will be thick, then what will, thin, the N-type, then what will happen? The light will enter to the depletion region very easily, because it's a thin surface it will get. So there are two reasons. One more reason is why this P-type is very, see, the mobility, diffusion rates of the electrons are higher. The electrons are more mobile in nature than holes. So therefore, when this N-type is thin and P-type is, it is larger, so the movement of the holes from the N-type to the P-type, when it will come to holes will come from the N-type to P-type, so it will be quickly, it should reach. If we'll make N as thick, then it will create a problem. Mobility of the holes will be very slow again. So anyway, so the major concept of N-type thin, because the light irradiance should reach to my depletion region as quick as possible, and P-type base is higher because thick. First of all, it gives a base. It will give a base because it will be on the downstairs, and the top the N-type layer is present. So down should be a little thick, and along with that, it will give more depletion region for creation of the electrons and hole pairs. So this much I can share with all of you what is the basic idea or knowledge how the light energy is converted to electrical energy. So what happens when this light falls? So this depletion region hole electron pairs, you may ask, so that light energy is sufficient to dislodge or break this pair and make the free electrons free, and this free electrons now easily can be attracted towards the polarity, positive polarity of the N region, and this holes will be attracted towards the negative region of my P-type silicon base, and as a result, so this will be negative charged terminal, and this will be positive charged terminal. Because why? These electrons will be collected by using these fingers. See here, these terminals, these are basically the fingers. Fingers means on the top of my silicon base, basically, so some rods are basically placed. These rods are basically conducting in nature. So these rods basically will try like this, fingers. So these rods are touching at every terminals of my n-type layer. So here it is touching, here it is touching. So these electrons will be cast by any one of the fingers. The fingers will try to collect the electrons. So what is the function of the finger? You can write the fingers are basically conducting material and it tries to collect the free electrons from the n-type surface, n-type silicon, and those free electrons are going to be passed through the bus bar. The bus bar means where all the free electrons are collected and it will be supplied to the outside circuit. And that terminal is known as minus terminal. And here on the top of it, we have the metallic body, that's a metallic bus, and where all the fingers are joined or connected. And here on the bottom of this PN junction or silicon cell, you have also another metallic plate which will collect the holes. Basically, the electrons will come from this side and it will enter to this side. So on both the sides of your PN junction, we have metallic structure. On the top we have metallic structure, the bottom also we have metallic structure. So as a result, due to this potential voltage difference which is created within this depletion region, to drive the free electrons to move to outside circuit, if you complete the circuit through a load. So this is a very simple fundamental thing, how the PN junction, how the solar cell works. And if you don't know this, I think that's why I thought that in this class we should know basic principle of operation of the solar cell and how does it works, how it converts the light energy to the electrical energy. See, there are so many amazing concepts which are already developed by this field. How to develop one silicon cell itself is one research field by the many physics scientists, many chemical engineers, many chemistry engineers. So they are working day and night how to make it very strong. But an electrical engineer, we talk about our electricity. We don't bother, okay, so you have given this material, it is fine. But how this material works, you tell me. This is in the material engineering, metallurgy also. In some context, even the Solanki, Dr. Solanki, he is not he's not in electrical background mostly. So he works on the material aspect of the device, like silicon device, what percentage will induce, how the free electrons will be more and more, how the depletion region will look like, what is its strength, what is its characteristics, so many. The electronics people also, they work a lot also in this direction. How to develop one good solar cell so that it will be more efficient, something like that. So this is whatever the material you have, the basic principle is remains same. The basic principle is we need some energy, so that energy is going to provide us the electrical energy. So finally our target is we need some electrical energy because this is the electrical source. So for our smart grid reason or smart grid technology, so we need some renewable sources. So that is how the solar cell provides energy with help of the light energy conversion. So this is how it works. And second, what are the advantages of this solar cell? The first advantage is it can be used either centralized or distributed power generation. So you can connect anywhere you like one solar panel. Already I have discussed in my last introduction class that near to my home also, on top of my building, I can connect the solar cell. Even I can make a solar park and I can distribute the 4 or 5 villages or 10 villages or 2 or some, we call it as remote microgrid system. Even I can also solar park where I can supply the power to the semi-urban cities, and also I can make some solar parks where I can supply the power to the urban cities. Okay, so it has a both. It's see actually why, because it is more or less it is geographical dependent, but fortunately 90% of our countries are sensitive towards the solar irradiance and we have sufficient solar irradiance, so there is not an issue for that. Okay, except the northern side. So other sides, other 3 regions are more or less very convenient place for the solar installation. So this energy independence and environmental compatible, of course, because the only thing I could say from my previous experience that the solar energy has impact. I am not denying. If some researchers, they are saying what is the impact of your solar system? Not many impacts, but major advantages It has minimal maintenance and have long service lifetime. 28 years, can you imagine? 20 to 28 years one solar panel can work for you. It is very amazing. See, these solar panels are installed in IIT Roorkee on the rooftop last 10 years. I could see this. It is installed by the Tata Power. So the maintenance is zero almost. So the up to 20 to 28 years, these panels will work for you. But where, and fuel sunlight is free for us, no noise, pollution is created from the operating PV systems, not from the PV panels. So the disadvantage of this is high cost. Yes, because now, but I will not. I am convinced, not convinced with this term, because we are trying to reduce the other. Because the solar panel, PV panel cost, when it will reduce, when the material cost will reduce, when its manufacturing industry cost will reduce. So now the manufacturing industries and the material industries, they're trying to reduce the cost to basically take the advantage of the solar energy, and the government is also trying to give some incentives and some kind of subsidies, that if somebody is going to have this industry and you will get this kind of subsidies. So you just propagate and you try to encourage the people so that the solar energy should come in a 100% manner. So more surface area. This is second disadvantage. It needs more surface area. Efficiency depends on the availability of sunlight. So I said the main and foremost drawback of this solar energy system is the non-availability of the sunlight. So this is very unpredicted in nature. You cannot say today I am just going to get 2 megawatt. Tomorrow, who knows? You may not get 2 megawatt. Even you get 0 also. If there is sunlight, there's a rainy day. So maybe you can get zero power supply from the solar energy system. So these are some of the advantages and disadvantages. And I can say that one more disadvantages which are coming now, the researchers, they are analyzing the industries which are actually engaged in basically developing the components of the solar energy system. Those industries actually consume energy, and from where this energy will come. So some researchers, they are saying they are using the coal-based generation, and some researchers, they are saying no. If you have a captive power plant, the captive power plant means the industry has its own generating system. So the captive power plant means is that if you have a own generating system, and that generating system itself is a solar, so they may argue again you have to generate those components from somewhere, something like this. So this chain is unlimited. I cannot say I'm not denying that the industries which are actually dependent some fossil fuel based energy to generate the components is also one question. So depending on that, the solar energy system more or less up to its efficiency is up to 15%, 16% maximum. It is not 50%. Wind has 35 more 40, but solar system till date is not that much of efficient due to all these regions. So this is still a very good research field, and researchers, they're trying to have more developed, advanced technology for this. So that's the generation of the solar cells, like first generation, second generation, third generation. So this first generation consists of large area, high quality, single junction device. Mostly the examples are silicon wafer based solar cell. And the second generation developed to address energy requirements and reduce cost of solar cells. There is thin film solar cell technology. And the third generation is advanced thin film solar cell technology. So these are some of the technologies. I am not going in deep of it. So these are some of the basically the very clear-cut picture of these solar cells. You can see how it is they're basically connected. This top layer, bottom layer, this N type, and P type, and then these are the conductors, top conductor and the bottom conductors. And this red one is your N type. And this blue one is the P type. So this all are together, they are merged. So types of PV technology we have PV cell type, we have crystalline silicon type, wafer based, thin film and spatial. And in the crystalline silicon based, we have polycrystalline and monocrystalline. As you have seen from the video that we have polycrystalline, monocrystalline is more efficient than the polycrystalline. And of course, the monocrystalline has other disadvantages, and polycrystalline has some advantages, some disadvantages. Mostly in industry till date, we are using the monocrystalline type, okay, crystalline silicon based. And thin film is also much nowadays it is also coming up, but still it is in industry it is not that much of favorable till date, and special like compound and semiconductor type gassium arsenic based. So they are some of the technologies, PV types technologies. Okay, so here is some kind of like some thought process, because mostly we use these two types and others aside. One is crystalline type cells and one is the thin film type cell. The crystalline type cells are basically made up of from ultra pure silicon raw materials, such as those are used in semiconductor chips, and this wafer typically 150 to 200 microns, 1/5 of millimeter thick. So this is very thick, very very thick. So 150 to 200 microns means it is quite, very thick. Thin. So this thin film is made by depositing layers of semiconductor material barely 0.3 to 2 micrometers thick onto a glass or stainless steel substrates. So those are called as thin film coating types. So there are different types of ideas, but crystalline type cells are basically used in the top of our buildings. Also, we have this monocrystalline type silicon cells, and where we are using the PV panels. So this monocrystalline silicon module efficiency is around 12.5 to 15%, and polycrystalline silicon based module solar cell modules cost is around 14%. Copper and cadmium, so many amorphous silicon. So therefore, the monocrystalline we prefer because its efficiency, module efficiency is better. So here are some of the pictures I have collected. This is monocrystalline, this is polycrystalline, flexible amorphous thin, GIGS. This is actually recent thin film type generation. This one, GIGS. Okay, so these are some of the things I have collected. Okay, so this is actually the glass rod. This is my electron array. This is my N-type silicon. This is P-type silicon, and this is the our rod. The backside metal. So these are basically bonded together. And then here my minus and plus sign. So from here I can take the power outside. So when you have a single cell, that single cell itself has the capacity of generating how much power? 0.3 to 0.6 volt. You can note down it. A single photovoltaic cell, I think all of you understand what is photo and what is voltaic. So photo means it is coming from connected with the electricity, sunlight energy. Voltaic means some PN junction that depletion is in reaction. And due to that, some barrier is photo. Sometimes we call it as photovoltaic. So photovoltaic means due to light incidence, we are creating some barrier. That voltage is known as photovoltaic. So that voltage, single photovoltaic cell voltage generation capacity is 0.3 to 0.6 volt, more or less 5.5 volt DC. It is the DC voltage. It is not AC voltage. So when these are the photovoltaic cells which are connected in series or parallel, we call it as module. So a single module can have many number of the solar cells which are connected in series together, again parallel, to make a single module. The single module which when they are connected in a parallel or series combination, we call it as solar panel. And when many solar panels are connected in series parallel, we call it as array. So this is how the things move. First is solar cell, a single cell, then module, then panel, then array. So this array is the complete power generating unit. So array, if you have arrays of your solar panel or a solar module, then it is a suitable point where we can generate more energy or more power. This is a complete power generating unit, consists of number of PV modules and panels together in series and parallel. So that is how I can show you here how the solar cells are connected in series and parallel. This is one example. Here you see. Suppose I have one module. I can show you the specification sheet of one module of the practical solar cell Tata Power. Also, I can show you how it is written. What are the specification of a solar module? You will ask in the company. So what they will give you and how you can rate them. Suppose I just I'll go to the market. I'll say 60 watt bulb. You please give me. So we never say that 230 volt. We call it as you give, or 50 hertz bulb you give me. We call it as 60 watt is bulb you give me. 100 watt is bulb you give me. So therefore, what are the kind of specifications we have to mention while purchasing a solar module? So before that, you should know how they are connected in series. and how to increase or decrease the current and voltage level. So each module, let us say it is 12 volt, 5 ampere, let us say. So if I connect in this manner, this is my plus terminal of the module and this is a negative terminal, then what will happen? 24 volt I can produce because these two are connected in series. So series connection happens inside the two modules. So the voltages are going to be added and current remains constant. And if I connect them in parallel, what will happen? The voltage remains constant, and then what will happen? The current will increase. So 5 plus 5 plus 5, that will go to be 15. So similarly, 96 volts and 5 ampere. So in this manner, we basically connect the solar panels to increase or decrease our voltage and current capacity depending on our requirement. So now series parallel combination. Suppose you have three panels are connected like this and three more panels are connected like this. So total 24 volts because this is 12 volt and this is 12 volt. So 12 volt, 24 volts in parallel. So 15 ampere, there is 3 in series, 5 ampere, 5 ampere, 5 ampere. So like this, we basically do the combinations of the solar panel and to have more energy or more power from the individual PV arrays, right? So array means it is a combination of many PV panels or modules. The panel means you have many modules are interconnected. So and now this is the operation of the PV system, how it operates. Like you have the solar energy system, this energy conversion which occurs here is it converts the light energy to the electrical energy. And this electrical energy is DC in nature and with a frequency of 0. So there is no frequency in case of DC. That is what all of you know it. So now this DC energy is going to be converted or conditioned using some some energy conversion conditioning system. And that energy conditioning system is nothing. You have the your that is your inverter, which converts the DC to AC energy. And that AC energy is having a frequency of 50 hertz. And that 50 hertz AC is going to be fed to your distribution system and to the loads, electric utility. So wherever we are interested. Again, here from the energy conversion process, either you have to convert this DC energy to the energy storage system. You have a battery connection near to your inverter system. So before the DC is entering output terminal of my solar panel is entering to the inverters. So before that, I will tap the DC system, DC energy to a battery. The battery will tap the DC energy from the solar panel. So when it is required, it will just charge the battery. And again, when the battery has surplus power, the solar system is absent, the battery will discharge the power through the inverter and the inverter will supply the power to the AC loads. Now, so these are types of solar PV systems. One is grid connected PV system and the other one is the off-grid solar system. So grid connected means the system is connected to the grid where you see it's a very simple PV modules and through the inverter, the DC voltage power is converted to AC. So with the help of this inverter, and this inverter output comes to the AC board. Here is my board supply system. And then it comes to the meter, and from the meter it goes to the substation or supply from power grid. Or else from this board it can go to my the other loads of my home appliances, and also I have a controller which will collect the data, monitor the system, and it can communicate to the outside. This is known as grid connected PV system. Why it is grid connected? Because I'm supplying some power, useful power inside my home, and some power I am just supplying to the nearby substation. So therefore it is a grid connected substation. Suppose I don't have any generation from the PV panel, then what will happen? I have to tap the power from the supply, the main supply. You can call it main supply and one is solar supply. You can see anybody, if you're interested, I can make some video for all of you how the solar panel is integrated in our distribution network. The grid is main grid supply is there in our building, every building, and again one more connection is coming from the rooftop mounted solar panel, and there is a main switch which is mounted inside or downstairs of my electrical building. So there the two connections are coming. When the solar power is not available, the main grid supply is going to be supplied to the loads. So these are some of the grid type connected system and off grid PV system. Off-grid is simple. It is very simple. We have PVRA and we are giving the charge controller. In the next class, I'll discuss what is charge controller and some DC supply is given to the battery bank. And then you have some DC loads and maybe you can connect to an inverter to supply the power to the AC loads. So these are some of the today's very basic class I took. Again, our class will move ahead like this. I'll talk about the modeling of the DC modules, the DC cells, mathematically how to model it, how it looks like this. So, and then also I'll do some mathematical calculations and its characteristics and other things. Slowly we'll learn about the PV power plants. So, any questions today's class? So, I'm ready to answer all your questions. Students, any questions from your side? Yes. You don't have any questions, so I'll go to my seat, attendance seat. Any questions, please?
Madam, it's Robin. Madam, can you send us the last module PPT? Last module.
Yeah, sure. So today I'll send, definitely. I got now added. So I was just waiting how many students are going to enroll for this course. So finally I got the list because our last date is over almost. I mean I got all the enrolled students, and I requested to the academic section that you add all the roll numbers to my EEN has this 672 at the IIT.ac.in. So whatever I want to communicate, suppose after few, maybe today I'll just post you some PDF files regarding the solar cell. So maybe an MPPT or maybe some buck boost converter. So I'll just share with all of you or wind system, whatever material I want to communicate, I can communicate with all of you so that you can read it and together. So it is also difficult for me also to communicate with all of you. So today is over. So tomorrow onwards, I'll send whatever the materials I have, I can communicate to all of you. But don't make it public. It's my request. Don't put in Facebook forum or somewhere. Just you communicate within your mail ID. It is my kind request. Yes, tell me. Any questions, further questions? No questions? So today is 22 September. So I have to take today's attendance quickly. Anyway, we could, download the attendance, but still, I'm just taking rapidly, quickly. Today's 22nd. Yes. Serial number 12, Deepak Kumar. Are you present?
Present.
Yeah. Okay, good. Gaurav Kumar.
Present, ma'am. Present, ma'am.
So Gaurav, you are present. So you got something to class? You are getting something from Smart Grid class or not?
Yes, ma'am.
You understand something or not? We expect more from you people. In the meantime, I'll give some assignments to you people. So I'm trying my best to class some basics. But you people have to help me more. Okay. So read well because this is a good course, very application oriented. Present. So next is Rahul Kumar. Rahul Kumar, are you present? Rahul, are you present? Absent Rahul. Silpa Meena. They're sleeping. Tanma Agarwal.
Present, ma'am.
Oh, he's our class representative, right?
Present, ma'am. Present.
Yeah, you're our class representative. Paryushu?
Yes, ma'am.
Oh, great. So what is your? Now all the students are.
Ma'am, actually, I sent the mail last day around 10 p.m.
I got it. I have added those words.
Okay, ma'am.
I have added, and to be honest,